Nice to meet you.
So, yesterday, we filled out some of the additional remaining features of core features of AnyLogic of relevance in the health space with a discussion of a key construct for agent-agent interaction, two-way networks. And we saw how we could choose within AnyLogic to situate agents within networks of several sorts. And we didn't dwell on it. Many other of my lectures online do. We systematically explore the implications for network structure and dynamics of a variety of network types. In brief, AnyLogic supports at a built-in level static, find my words there, static networks, unchanging networks with respect to about 6 of them or so. One of them is what's called a ring lattice network, where once agents are situated, agents are aligned in a linear fashion, so there's an ordering, 1, 2, 3, 4, 5, 6, etc., amongst the agents. And agents are connected with others on either side of themselves in this ordering. So agent 3 might be connected with agent 2 and agent 4, for example. Or agent 3 might be connected with agent 1 and 2 on the one side, and 3 and 4 on the other. Okay. That's called a ring lattice network. And that's an extremely localized structure. And there's a 2D version of that that we did use, called a distance-based network, where any two agents are connected if the distance between them falls within a certain threshold. So if they're no more than a kilometer apart, they'll be connected. So those are very localized networks. On the one hand, in one dimension, I'm connected with people who are no more than one person apart from me on either side in a kind of one-dimensional ring. On the other hand, in 2D space. So those are very localized networks. On the opposite extreme, AnyLogic supports what is probably the most common type of network you'll see out there in the literature for theoretic studies, which variously goes by the name of a Bernoulli random network, a Poisson network, an Erdos random network, or sometimes just call it random network, as is done in AnyLogic. And there, if you consider any two people in the population, they're connected with equal probability. It has no regards for, no interest in propinquity. It has no attempt to connect people if they're closer together in space or closer together in their characteristics. Rather, any pair of people, pair of agents, is equally likely to be connected. So that's the extreme of global connections. There's no paying attention at all to their location. In contrast, the ones I first introduced, the ring lattice or the 2D, locality is everything. You're only connected with people nearby you in some sense. Nearby you in this ring, or nearby you in 2D space. In between is something that is called a small world network, where you're connected mostly with local people typically, but a certain fraction of your connections are with arbitrarily chosen people out there in the general population. So I have most of my connections are with people nearby in a 1D sense, a ring lattice sense. But then perhaps 5% of my connections are with people across the network. And it turns out that 5%, when I talk about the tag wagging the wog, the dog. If I talk about the tail wagging the dog, often those 5% of connections, or it could be 1%, make all the difference. Changes it dramatically from a ring lattice dynamics to something more similar to a a random network dynamic. So just a few long-distance connections can make a huge difference. And you may have heard in popular press about these things with the idea of 6 degrees of separation. You know, if you pick out an arbitrary person in the world, chances are that anyone in this room could be connected to them in roughly 6 links through connections of some sort. So you might know someone who's from, maybe it's someone in West Africa, and you know someone who's from East Africa, and they know someone who does occasional business in West Africa, and they'll know someone else who is closer to that tribal area or what have you. Anyway, so those are a couple types of networks. AnyLogic also supports a very theoretically important construct called a scale-free network. And this is a network of great interest theoretically and of great practical interest in many areas because it captures patterns in terms of a power law distribution for the number of connections a given individual will have that are seen throughout nature and throughout human systems and social systems. And it's associated with a process where the presence of some resource makes it more likely you'll acquire more of that resource compared to someone who has less. Wealth acquisition in many economies is unfortunately like this. It's kind of a perverse golden rule. Those with the gold get to make the rules, and they can get gold more easily. We see it with internet search engines. So if a site has people coming to it, it's more likely that people will be searching for it, and even more people will come to it, and it'll be ranked higher yet in the search engines, and yet more people will come to it. So it leads to this sort of power law distribution where a few sites have tons and tons of connections to them, and then there's a long tail. I should say there's a long tail in the sense that a few sites have tons and tons of connections, but most sites have very smaller numbers of connections. And so it is with a lot of human networks. When it comes to sexual connection networks, there's a surprising amount of power law variation. The notion of scale-free comes because if you consider a given number of connections, call it K, and consider the probability of observing that number of connections compared to 2K, 2 times K. So imagine having 2 connections compared to 4. The ratio of those probabilities is going to be, of 2K to K, is going to be the same independent of K. So 4 to 2, how much more likely it is to have 2 connections compared to 4? It's the same ratio as how much more likely it is to have 100 compared to 200. Now, there's limits to scale-free networks in terms of human systems. They break down, at some point way out there in terms of small numbers and in terms of the goodness of the fit to characteristics. But we've observed scale-free with our smartphone-based sensing work, with our work with mobile technologies to inform our health system. For those who are not familiar with it, we have a system which is now used by partners across the world to collect data related to health behaviors, in large part to inform our modeling, but also to inform other aspects of understanding of health behavior. And many of the types of data we pick up there are suggestive of power law sort of characteristics of that behavior, such as in length of contacts, such as in the number of contacts you have, even brief contacts in the course of the day. And there's some intriguing features involving statistics in the mobility space as well that have been suggested as having a scale-free character, although we've since challenged that. So AnyLogic supports these types of networks, and if we had looked yesterday, if we had poked around for example, if we had gone to, well, let me ask this. So if we're considering networks of persons in that model we built yesterday, that hierarchical model, where would the network structural assumptions be specified in any logic? Does anyone remember? For one of those persons, what were they in? They were embedded in a what? In a, it was a hierarchical model, so they were in a city. And where was it declared what sort of network you want to have for those people? We went through it quickly, and I didn't emphasize it like I should have. Where was that specified? Well, it turns out it was in city. So if we clicked on city for that model and we had scrolled down, we would have seen here over in properties that the network type is set to distance-based. And you could see these other ones I've been describing here. You'll also see there's a user-defined network. And I promised Betsy that in the course of the boot camp, before the week is out, I would demonstrate dynamic networks. And those are put into place most commonly with a user-defined network. You could actually start with a distance-based network and then add connections to it. The only problem with that is when you say apply network, it will sort of bring it back to a distance-based purely. It'll throw away the extra connections, which is sometimes not what you want. So there's this thing called the user-defined network, which allows you to specify precisely your choice of connections. When the model's running, you connect to people, you disconnect them. And we'll see how that can be done in a little example sometime in the next day. Yeah.
So I understand that, so small world and scale free are defined differently, but it would be theoretically possible to have a network that is both. And I didn't know if I mean, I don't think it would be easy to do from a drop-down menu, but if you've ever tried to do something like that.
It's a good question. So, and as is not infrequent, I will gladly display my, confess my ignorance with respect to some of the details of this. But both small worlds and both the technical small world network, which is also called the Duncan-Watts network, Strogatz-Watts Watts-Strogatz network. It's named after Duncan Watts, who was actually an Australian graduate student of Steve Strogatz at Cornell, that type of network is commonly placed. As I understand it, it's placed in the clade of networks that do include scale-free networks as well, in the sense that you can have large spanning networks where you can have few connections between many pairs of people. And there's a whole class of what are called exponential random graph networks, which generalize this notion in an extremely powerful way. And with a single sort of theoretic or a single formalism, you can simultaneously embrace a broad sort of class of networks, including scale-free and small world network, etc. Now, Jeff and I have been trying to get AnyLogic to explicitly represent exponential random graph networks, which are at the cutting edge of practical application of graph theory for many years now. And I see Scott says he's been trying to as well.
I sent them the algorithms for the creation of the networks like years ago. I'll just say that really quick also. Exponential random graph models really need to be implemented before you can do a lot of network experimentation. Because basic network analysis will tell you that networks are random, and you cannot create, even using the small scale-free networks here that AnyLogic gives you, those aren't necessarily representative of your network. So exponential random graph models, the entire point of them is to be able to create networks that can be used as an error term for statistical analysis compared to what you're doing.
So they're very well fit to empirical data. You can have them, they'll be better fit than the built-in ones. Now, the built-in ones are very useful for sort of quickly testing the robustness of your algorithms to network assumptions. So for example, and Yuan Tian will be giving a talk here tomorrow. She's the modeler who's heading up our Ministry of Health's E-Rates and Patient Flow project, and the modeling side of it. And she's going to be giving a talk here tomorrow. She's also, I'm delighted to say, she's joining Scott as a doctoral student in our program as of about 10 days from now, while continuing to work out at my Scott as well. She has actually done some very nice work with representing contact tracing processes, particularly for TB, and amongst other things, looking at the effective network structure on the effectiveness of these. And it was very handy in any lab to be able to quickly go between different network structures, impose alternative assumptions, test the robustness of the algorithms. But for really rich, for taking a model that is empirically grounded and matching up with network characteristics that are collected from the population, you'll typically need to go beyond this. And in fact, in Yuan's thesis, she needed to go beyond it, even for things like for scale-free network, just to be able to incorporate new people coming into the population and et cetera, rather than saying, sort of reimpose a scale-free network, which can be totally different than the last one. It wouldn't respect, when you say .apply network, when a new person came in like we did, it wouldn't respect the old network connections. She had her own little algorithms, and like Scott said, it's been our observation to incorporate empirical data like we get from our smartphones or what have you. You really want to have a bit of your code that will build up these connections. The good news, that's the bad news. The good news is that it's not hard to do. I mean, at a level of code, it's not terribly hard. And as Scott says, there are published algorithms that will allow you to tap into a lot of theory with depth in the network area without a huge amount of complication. I'm not holding my breath while any logic builds this feature, and it may happen, but it will. If it happens, it'll probably happen in the fullness of time. Yes.
What is the name of the network you guys?
Exponential random graph, ERGs. Yeah. So the king of networks in our lab is unreservedly Winchell. I mean, very clearly it's Winchell. And he's done a tremendous amount of work with empirical network data from smartphones and data of the sort you can get from cell towers, and has combined it with simulation modeling in some very interesting ways. He is likely to be talking this afternoon not on this topic, as part of the lunch presentations. Okay. Winchell attend. He's one of our senior graduate students, and will be graduating shortly. Okay, so networks are extremely important. We'll come back to this issue of dynamic networks and look at building in connections to them. As in most things, if there's portions of our work that are responsive and you want to see if you could draw on things, you're welcome to speak with Winchell or myself, and we can provide you, past examples of models we built or what have you. Okay. So that was networks, and we saw that agents could communicate in networks using what? What construct allowed them to communicate in networks? Messages, indeed, ladies and gentlemen. So if we had gone to person here, we'd see that, for example, exposure was carried out on a particular message, and when a person was infected, they were sending messages to others. This was very pathogen-oriented, but it could represent contagion of ideas, knowledge, norms, and attitudes. And so this general notion that there's a discrete instant or a discrete contact which might or might not influence another person is a very general idea. And it transcends, whether it's pathogens or ideas or rumors or memes or what have you. And messages provide a very elegant way of accomplishing that. And, I didn't emphasize it, but the model that we had, we could have chosen different semantics, different kind of meaning of how we could have sent messages not just to a randomly connected person, but to all connected people, everyone in their network. So maybe they have a network composed of lab mates, and they cough and sneeze, and the lab mates are all exposed simultaneously to pathogen, rather than just being a single randomly connected person. We could have easily had that, and any logic will gladly support those many types of interactions. One thing I didn't emphasize, but will be of relevant when we discuss spatial layout, is this notion of neighbor is different. Often in networks, we do speak about neighbors in a network, but neighbor in any logic is particularly referring to neighbor in what's called a discrete space. So when space is divided up into grid cells, and so you have a gridded space, and you're in one cell, and there's people north, south, east, west, and possibly northeast, northwest, southeast, southwest of you. Those are called neighbors in space. And so if you want to send it to network neighbors, you do it with connected, random connected, all connected. You can also send messages to all. Neighbors are reserved for that case of discrete space, okay? Space which is divided up into cells. And I provided you with some models which make use of that space, such as for dynamics in a hybrid model, dynamics within a cell spreading to neighboring cells. Yes, Chris?
Does that logic extend to the GIS context? Is there cell?
No, there's regrettably, although this may have been something I was poking any logic about. I think I did a couple of years back. But often we do like to have cells superimposed on, or at least some sort of structure, maybe it could be hexagons or what have you, overlaid on a GIS to capture certain dynamics. So Cheryl is responsible for the best unpublished model I know in any logic, which really, which I love. It's one of my favorite models. Unfortunately, for a variety of reasons, it hasn't yet reached an important publication, which is a model of chronic wasting disease, where we actually have a set of gridded cells superimposed on a spatial region, and the original model wasn't GIS, although a later adaptation made it GIS. But the point is, by keeping track of grids superimposed, you can keep track of the amount of prion, these kind of misfolded proteins that are shed that are contaminating that portion of the model. And that's a very powerful notion. It may be that you want to impose a grid associated with the amount of MRSA that's been built up in a certain area of a spatial layout, for example. Now, GIS databases do maintain some maps that could be used for that, but we wanted any logic to add the ability to transparently add a sort of layer of structure where you could change things. And I'm not aware that they've added that. Scott, are you aware that they've added anything like that in their GIS?
Not really.
Yeah.
I know that if you really dig deep into the code base of GIS, you can do a lot of amazing things with it.
Yeah.
But it takes quite a bit of code knowledge.
Yeah. Yeah. So if anyone's interested in seeing a model like that, I could show you that one. Although my recollection is it needs some. The original version needs some updating for AnyLogic 7. The other one that's of relevance is a model whose details I don't recommend, but it's a fun model to look at in the example models area called wandering elephants. And there you have a grid of vegetation that's overlaid on the model surface, and there's dynamics in that grid. But right now, that's the notion of a sort of grid in space is unfortunately not supported right now, to the best of my knowledge, in GIS in an easy-to-access capacity, at least. Now, could it be done? Yeah, you bet. I mean, you take a wind chill, and if you brought him a GIS model, within 15 minutes you could have a grid superimposed on that. It's not a big deal for someone who's comfortable with code, but we prefer to lower those barriers so everyone could do it declaratively. Just say, make a grid happen. And so you don't need a wind chill in your back pocket, although all of us could benefit from one. Yeah. In any case, hope that comment is helpful. Okay, ladies and gentlemen, so we saw messages, and messages were used to communicate, but we also saw a hierarchical structure. So we had persons within cities and cities within the main, and that could have been 5 levels. It could have been 7 levels. It could have been 2 levels or 3 levels. AnyLogic is quite supportive. The notion of that person has to be in main is not true. It could be in city, and city could be in region, etc. We for simplicity or for due to time, limited it to just 2 levels or 3 levels here: person, city. But we also saw expansions earlier. We could use variables to sort of color states and then and then use that to indicate their visual representation, right? How we could use experiments to sort of encode alternative assumptions to these, and sometimes we put parameters in main that we wish didn't have to live there conceptually. Things like duration of infectiousness, duration of immunity. Conceptually, those are parameters about a person, and it would be more fitting, more appropriate, more elegant, more conceptually sort of suitable if those were at the level of person. But because they didn't vary by person, because we wanted them to be able to be changed on a per experiment basis, we put them in main. And then that allows us to specify them for different experiments. Does that make sense? Okay. So that was some features of the model. You also saw me engage in several bouts of debugging, which were good. You'll notice that I have switched now, even as I speak unto you, I've switched over to my Windows version of AnyLogic, which I find to be less buggy than. When I say buggy, the Linux version isn't horribly so, but it definitely got more glitches, and it occasionally bombs out, like you saw that once or twice yesterday, or at least the Java people did. So I prefer working on the Windows or Mac version for robustness. Linux is not foremost in AnyLogic's priorities. Okay. So those are some features of that. You saw that when I was debugging, what I would do is I develop a hypothesis, I put in place a mechanism, and often it was as simple as a printing out statement to just sort of see if I could test that hypothesis, often falsify that hypothesis. And based on the observation that would either further my conviction that might be what's going on, or point me in a different direction. And if you do that, it's kind of like you're looking for, the analogy that's used in software engineering is a wolf fence. So you're looking for a wolf in all of the Yukon. Traditionally, it's been used for Alaska, but here we're in Canada, so I'll say Yukon. And you know, you look for a single wolf there. Somewhere there's this bug, you don't know where it is, and you put a fence across the Yukon, and basically you see which side it's located, and then you draw a fence against to have that side, and then you see where it's located. And pretty quickly you can zoom in on where this wolf has got to be. And so it is with these programs. You've kind of put a few sort of indicators to indicate where it is, and you can quickly zoom in on what it might be. But you're always developing hypotheses about what might be happening. And in that case, we saw that it had to do with this. Within a person, we had connections. And I should probably mention this because we're not going to get time to see me build models with it, but there are models I have provided to you which make use of this in a more general construct. These connections, this was as of version 7, I think they folded this in. And I believe, although I don't know with complete certainty, that this was a result of Jeff and Mike poking at them. We said, look, in health, we need multiple types of networks, okay? There's people who use intravenous drugs together, and then there's family networks, and they need more than one network to maintain this. And, you know, a given person may be enmeshed in 3 different networks. And previously, AnyLogic didn't support that in a transparent fashion. You had to write a lot of code. But then they folded in connections. Now, it's not obvious why this is advanced, putting connections in visually. Well, there's a couple things about it. One of them related to another problem that happened in our boot camps, which is that it used to be a problem to kind of easily draw these connections. And I'd have to engage my audience in mathematical kind of envisioning in order to have them do it. Now, you go to these connections, you could simply go to animation, say draw a line connecting agents, and it's easier than it used to be. So that was nice. It turns out that by explicitly allowing us to pick to whom a given person is connected, it also can ease certain traditional troubles. And importantly, we can also choose to what state charts messages should go. In addition to these built-in connections, which are the ones that are frobbed by when you say, like, I want to have a scale-free network or Poisson random network, you can actually drag in additional connection types, which basically represent different types of networks in which I'm associated. So I might have a family network, I might have an IDU network, I might have a sexual connection network, and I might have a collegial connection network. And all of those would be different connection types. They all might be associated with different colors of visualization and different semantics in terms of when you send a message over that network, which state charts get that message. So it provides a nice way to capture multiple types of network structures simultaneously. And if I'm not mistaken, 1 or 2 of our models that we provided to you make use of that and show how it can be used. In fact, I'm 96% certain. And if anyone's interested, I could point you to these. These connections, the ability to have multiple types of networks is really valuable. Now, yesterday, the bug was that somehow we had a connection network where every one of these was not clicked. And I'm not sure how that happened. A student going forensically over the video might be able to find out if I accidentally misclicked somewhere or what have you. But in any case, you occasionally will need to check, is this connection passing on the message to state charts? Indeed. And that's where you'd look for it. Okay? It's these connections. You notice you could frob the connection properties to prettify your model. Okay. Great. So, in case you folks are wondering from out of Canada, frob and prettify are not Canadian expressions. They are geekies expressions that I have largely imported from MIT. So Cheryl probably finds them just as foreign as you do. Okay, ladies and gentlemen, that's our retrospective for today. Any questions about what we did yesterday? Okay, today we have an exciting day ahead of us, at least by